Hello, everyone. So I'm Artie. I'm the president of CompSoc, as some of you may know. So today we have two wonderful talks with a pizza break in the middle. So first of all, I'd have to ask you all to scan the QR codes at your tables or a table near you, just for track and trace reasons, because we're at Deviate. So our first talk today is from Dr. Petros Papapanagiotou. Oh, sorry. So our first talk today is from Sethu Kumar, and it will be on AI and from automation to autonomy. So everyone give a warm welcome, please. Sorry.
Can you all hear me up there? Yep, excellent. So I guess most of you are here for some pizza. I'm here for the same thing. But before we get to the pizza, I hope I can show you a little bit of the exciting work that we're doing at the School of Informatics within the department that deals with AI, robotics. So I presume a majority of you are enrolled for informatics courses, but I guess you also have some members from out with of informatics. Robotics has actually grown as something that we've been trying to do for the past 10, 15 years in informatics. And traditionally, robotics sits in the engineering department, but the nature of robotics that we do at Edinburgh is quite unique in the sense that we do robotics that marries what people call data science and machine learning these days with the traditional areas of control and planning. So you will see that flavor of robotics in my talk here today. Again, if you have any questions, do feel free to put your hand up, interrupt me. I'm very happy to take questions in between and definitely at the end. So this is meant to be an interactive talk. And also, I brought a little prop along with me, so I'll need 2 volunteers to test something out. So if you're keen, please make sure you put your hands up early. Okay, so the title of today's, well, I wouldn't call it talk, it's a little dialogue with you guys, is From Automation to Autonomy. And people often confuse what automation is and what autonomy is. So automation is what we've been doing for ages. Creating robots that can do repeated things again and again, build our cars for us. Autonomy is something slightly more fancier, slightly more exotic. It's where machines can start making decisions on their own. When they can start, you can start having AI built into these kind of devices where it's not just doing what you've told it to do, but has almost start having a mind of its own by evolving its behaviors. So if you think about, by the way, is there a way to sort of dim the top lights so that this, I think some of these slides will look better then? Yeah, okay, perfect. Robotics is becoming ubiquitous in various walks of life. Some of the things you will recognize as traditional areas like manufacturing, self-driving cars, autonomous cars, smart cities, healthcare, care for the aged. But there are also some more exciting new areas like in space, in underwater mining for rare earth materials. Does anybody here recognize what the third panel from the top, the blue panel is? Any guesses? Anybody? No? Yep. Sorry, can you speak up? It's not underwater, no. It's something quite crucial for our power production. So this is the inside of a nuclear core, inside of a nuclear power plant. And basically, when we rely on the nuclear power plant for our energy, but also it becomes a liability when we have to decommission those plants. And so Sellafield is one of the biggest sort of places where you've got lots and lots of radioactive waste which we need to handle, and robotics is crucial for something like that. So if you look at where robotics has been, so traditionally robotics is the way we program robots is by what we call teleoperation, or programming it to mimic some behaviors. But now the research is going more towards autonomous behaviors, where we're getting robots to behave and move and change its actions based on some autonomous aspects. But really, for the next sort of 10 to 15 years, the real challenge is going to be what we call shared autonomy, where we can seamlessly move between the two ends of teleoperation and the robots making autonomous decisions on its own. And I'll give you a few examples of that going forward. And I'll also show you a real-life example of an autonomous behavior using this prosthetic hand in a live demo. So one might ask, why do we need robotics at all? Why do we care about using robotics, and what are the scientific reasons for doing that? But before we get to that, as opposed to fully autonomous systems that we've been touting for ages, there are some real challenges for getting to full autonomy, and the reason why I'm saying shared autonomy is important is because of these reasons. So robots of the next generation will need to interact closely with multiple objects, will need to deal with noisy sensing, it'll need to deal with real-world dynamics. You have highly unconstrained environments, and more importantly, when humans and robots are interacting, you've got to take into account human intentions while incorporating the behaviors or changing the behaviors of the robots. But there's also another sort of socioeconomic reasons why we need robots. Why can we not have robots? And that is to address some of the grand challenges. So things like dealing with the industrial demands in a sustainable way, dealing with food security for a growing population. If we have our tall buildings and metros and large structures like bridges, we need inspection, repair, and maintenance of these structures, and we need robots to be able to do that at scale. Another big area is healthcare and aging, and over the past 2 years, many of us have already experienced the importance and the need for flexible redeployment. So if you want to work from home, or if you want to make a factory operate as normal while sitting in the comfort of your living room or your office, this notion of remote operation, telepresence, and sort of semi-autonomous behavior has become very important. Okay, so let me start by giving you an example of a shared autonomous behavior. So imagine a scenario where you are trying to operate a robot like that. You'll see a video in a moment. And the panel that you see on the right is the console that you'll see is, on your computer monitor. And what's happening here is the robot has a digital twin of itself. It basically builds from real-time perception and sensing a percept of the world. It's got a little camera that it sees, and then that's the actual robot doing the behaviors. So in this scenario, what's happening is the robot is making lots of decisions autonomously on its own. How to avoid bumping into obstacles, which hand to use to pick up things, which hand to use to remove debris, clear its way, and then navigate a path to the goal. The only thing the human is doing is giving some high-level instructions, high-level volition of pick up this object and put it there, using some 6D mouse or something like that. So this is an example, a perfect example of shared autonomy. We also call it punctuated autonomy, where the low-level decision-making is done by the robots, but the humans are still in charge of the high-level sort of planning and contextual decision-making. And that's very important because we can get scenarios where fully autonomous behaviors don't work. So where do these kind of, where can you apply these kind of scenarios? Where are these things relevant? So you can apply this to the nuclear decommissioning scenario I mentioned very briefly earlier. There's been lots of work in sending robots to disaster recovery scenarios, collaborative manufacturing, where robots and humans work much more closely together. Also, those of you who've been to London over the past couple of years, you must have seen there's lots of, there's a big hole they were digging underneath London. There was while making sure the city does not shut down. And that's the Crossrail project. So the Crossrail project involved digging massive new bores underneath a working city with metro systems working just parallel to each other. And they had these things called shotcreting machines, which would spray concrete. And to be able to do that, you had to have very skilled technicians or workers who need to be trained for a long time. And still there are lots of mishaps and lots of accidents. So shared autonomy systems can be very useful. And some of the things that we're doing here, we deploy here, they are very useful in still allowing the human to be directing how the spraying happens, but preventing them from doing something disastrous, like hitting a live cable or spraying too thickly on a particular place where you've already sprayed. So it can act as a sort of fail-safe to make this happen very efficiently. So this kind of robots are most useful so one of the areas, some of the projects that we have involves robots working in extreme environments, in environments that humans don't want to be. And one of these extreme environments is an offshore oil and gas platform or a maintenance of a renewable offshore energy setting, where workers typically have to spend the order of 6 weeks on and off the rig in pretty harsh conditions. So the idea is, if you have robots that can largely take care of the inspection and maintenance aspects. So you'll see a video here of a robot, the four-legged robot navigating in scenarios that are not designed for wheels. So you can clearly see there's lots of obstacles. Humans are very good at navigating this, but if you want a wheeled robot to navigate this environment or this scenario, it's pretty hard. So here's an example of some of our robots going and navigating steps, working in pretty hazardous conditions, so slippery conditions. And the real challenge for us as people in informatics is, of course, building the hardware, but also programming it to do this kind of planning, recover from failures, and ensure that you've got a system that completes the cycle, the perception action cycle. So I'm going to skip this for the moment and go on to, so that was inspection, repair, and maintenance. There's another very exotic project that we're involved in, and we are the only department or group in the world who are dealing with this kind of challenge. The only one in Europe having the NASA Valkyrie robot. This summit, the one at MIT, there's one at the Johnson Space Center, but you'll see in a moment the humanoid robot. But before that, before I show you that, one of the challenges is to, if you look at missions that NASA are running, they have got low Earth trajectories, then they've got Moon, they've got Mars, and they've got ambitions to go further. And you might have sort of seen in science fiction movies, the bigger these missions are, you need behaviors, you need capabilities that can be maintained and run, and so astronauts cannot stay there all the time. So they need facilities where this can be maintained and run. So that's the challenge for, oops.
Now meet.
Okay, let me just show you this video.
Now meet Valkyrie. It's a NASA robot worth over £1.5 million, which has just been delivered to researchers at Edinburgh University. Their task, to program it to act like a human so it can carry out space exploration that's just too dangerous for astronauts. Our science reporter Victoria Gill has had exclusive access to the robot and the team.
250 miles above the planet, the International Space Station has been home to more than 200 astronauts and one robonaut. But the next generation of this type of robot is being developed back on planet Earth, and it makes this one look quite retro.
You are looking through the eyes of a very human-like robot. This
is Valkyrie. It's NASA's 6-foot humanoid. It's designed to work in disaster zones and even go to space. But it's just arrived here at the Edinburgh Centre for Robotics so that programmers here can push the boundaries of how humans and robots work together. Worth in excess of £1.5 million, with 44 movable joints, scanning lasers and cameras to simulate human vision, this is NASA's most advanced humanoid.
Valkyrie is an amazing and unique piece of hardware because there are only 3 of its kind in the world.
But the team here has to create a set of instructions that will allow this robot to understand how to use its body to carry out every new task.
You need to make it do the things that we take for granted. For you and me, for walking, balancing, dexterous manipulation, it comes to us naturally. For getting a robot to do something like that takes a lot of effort.
With a core set of human skills, Valkyrie could be put to work in unpredictable environments.
I'd like it to be able to do very benign things, everyday actions, to be able to do what a human being does, to be able to mitigate situations that happen sometimes in a disaster relief, for example, Fukushima, to be able to do maintenance on the International Space Station is what NASA are interested in.
It's hoped that humanoids like Valkyrie could be sent ahead of human astronauts to explore the surface of Mars. But this very young robot is still learning. It takes several attempts to master every new skill. The ability to control its balance and motion, though, could have an impact much closer to home.
Doing research on a human-like robot, that can nicely feed into technologies that are very relevant socially. So, for example, some of the work on exoskeletons for support of human disabilities, things like prosthetics for people who have lost a limb.
The ambition for Valkyrie's future is beyond this planet. But this work could also lead to technologies that could change and even save human lives. Victoria Gill, BBC News, Edinburgh.
So that was almost 2 years ago, and since we made some good progress with not just this kind of robot, but also other humanoids. We've got one more humanoid in our robot in a robot lab, and you can see here some work that we're doing on robot navigation, stepping on sort of uneven terrain, walking on terrain that is not flat. And so the idea is this combines the full loop of perception, planning, real-time control in order to sort of, get a complex full body behavior going. So if you think about it, it's kind of programming these individual behaviors or individual motors, but getting all of these things coordinated in a way that real-time coordinated behavior happens on the fly. So that's the kind of system challenge, if you may. So just to give you guys, and I'm just going to run through this because this is late evening, Friday, so it's not a time for math or anything like that. But just to give you a perception of what it takes to do something like that. So this is what a robot sees. If those of you who have used LiDARs, they would know that. So this is what, when a robot scans its head, these are the LiDAR information, the 3D point cloud information that comes from this. So you've got to go from this percept to something that involves creating affordances, creating objects that can be grasped and moved, and do something like that. So this is some work that we've done on perception, about grasping an object, tracking an object in real time under clutter, and then being able to adjust the behavior of an arm in response to something that moves. So these are examples of settings where the behavior is not pre-programmed. So if you go back to what I just said, it is not pre-programmed behavior. It is settings where you're actually reacting to the real-world environment under changes. So this is with a lot of occlusion. We also need to do this when the robot needs to actually, for example, if the camera moves, we need to repeat the same thing under a non-stationary camera, for example. So another big challenge is representation. So if you think about Euclidean spaces and representing spaces in representing movements, but typically we do programming or we express our desires in terms of put an object from this table onto this part of the table, or underneath it. So we've been using concepts from topology. So if those of you are mathematicians, we use concepts of topology to give targets. So for example, if a robot needs to reach into a box, by using concept of topology, you can define what is inside and outside a box. So when the box moves, the concept of what is inside and outside moves with the box. So then we can, without explicitly replanning, we can adjust its behavior in response to a dynamic environment like this. So this is an example where it's not the classical representation, the classical programming. There's an interesting concept from mathematics of representation that is helping us adjust to dynamic environments, for example. Okay, I'm going to skip this and this. And okay, so one math slide for you guys. So how do we actually program something like that? How do we actually get a behavior like that? So for example, if you build a system, a robotic system like this with different motors and joints, so these are examples of our legs and actuators and arms that we built in our lab as prototypes. Now, if you want it to make a particular kind of behavior, like throwing or walking, then how do we actually program something like that? So the first thing to do is to define a behavior that comes under planning, right? Not control, but planning. And under that, you have to define what is a goodness function. So what is good behavior and what's bad behavior? And that's captured by things like this. So you need 3 ingredients. You need, first of all, a model of the equipment that you are controlling. So what is a model? A model is if I put an input X, what's going to come out? If I put a particular force to this joint, what's going to happen to the state of the world? Okay, so you need to build a model of the robot. Typically, these models are given at the time. You can kind of get it from the manufacturers and modify it when you add loads and things like that. Then you need a control objective. So you need to say, what do you need the robot to do? It needs to balance itself. So falling down is bad. You penalize it. Staying upright and reaching for a target is good. So you give cost functions that reflect that behavior. And then you have to apply, then you have to solve this problem. So you've got to apply a control algorithm. It's called the optimal control paradigm using probabilistic inference to then come up with torques that will optimize an objective and make it walk and do things that you want it to do based on the model of the object or the robot that you're programming. So these are the basic ingredients of what it takes to program a robot. Now, obviously, the devil's in the detail in terms of how do we get the algorithm to converge? Well, what are the right cost functions to define a behavior? Some of them are non-intuitive. And what happens if there's a mismatch between your model and the real world? So these are the kind of scientific challenges that we've got to address. I'm going to skip this, and I'm going to straight away jump to, so if we have a model of the robot, and we get it to behave in a particular way, then we can get very interesting behaviors like this. So for example, we can get a robot to behave in a very compliant fashion, in a very sort of springy fashion, while being able to support its weight. And why is that important? If you go to one of the kind of key things, when you've got human-robot interaction, you need these interactions to be very safe. So you can get behaviors which are compliant in one direction or the other. Okay, and we can also get behaviors. So just like we do legged robots, we can get behaviors where you can get 4 different distributed robots to work together to manipulate a load. So these are examples where you've got shared control, shared manipulation capabilities for controlling an object. And not just that, if I change the nature of the object that is being manipulated, if I add a weight to it, then a learning algorithm can automatically compensate for that and adjust its behavior to compensate for that weight. So these are examples of scenarios. Again, it goes back to my original goal of not just doing pre-programmed behaviors, but being able to adjust the behaviors in response to something that's changing in the environment that's dynamic. So one other fun thing, and this is, so this slide is more about something fun that I've tried very, very many years ago, and it's still very valid, and that shows that some of the core sciences that you learn, whether you do it in an undergraduate degree or whether you do it in a sort of master's degree or whatever, that kind of, if you are doing something quite nice and fundamental, those things are going to be relevant a long time going forward. So this is done, you can see 2005, this was published 2005, so it's probably done in the early 2000s when we were working on, this is doing my PhD. So one of the things we did there back then was how do we get robots to learn behaviors? So humans, when we're babies, we kind of do what we call motor babbling, and soon the babies, as they grow up, they learn to control their arms and legs very well so that you can do very complex behaviors. So the question is, can we do similar things where a robot arm doesn't know exactly what forces to apply to make a particular movement, but by doing motor babbling, it can collect enough data to understand the relationship between the force that's being applied and the consequence of its action. So once it does that, so this is very non-traditional way of programming a robot, because this is about using experience and learning, things like reinforcement learning, learning from data, to understand the dynamics of a robot arm. So once we do that, we can do something even more fancy. You can get a robot to learn how to balance a pole from scratch. So this is an example of a robot. It knows what is good and bad in terms of that being straight is good, falling down is bad. It does different actions and sees the consequence of its actions on the pole, and it learns a cost function-based behavior that eventually learns how to balance the pole without programming it from scratch. And this is okay, balancing a pole is not so exciting in the big scheme of things, but this is a very interesting example of how you can create a percept or create a paradigm where data-driven learning can lead to very interesting results. Okay, I'm going to skip this. I'm also going to skip this. And yeah, so now where do these kind of things, where can we kind of apply these kind of things? So one of the areas we've been working with is the Honda Research Institute, working with settings like this, where people have to work in very complex sort of assembly lines, lifting heavy loads. So one of the challenges that was set to us by the Honda Research Institute, this is in Offenbach in Germany, is can we get robots and humans to work collaboratively so that we can, first of all, avoid injuries to humans, but also ensure that the humans don't have to lift heavy loads and create problems with their bodies. So this is early days of our research. So what is the most challenging aspect in this research, as opposed to two robots manipulating an object that we saw before? The biggest challenge is it's very hard for the robot to read the mind of the person who is operating the device. So you and me, when we co-manipulate an object, we are very good at using social cues to do things like, the kind of piano movers problem. So we are very good at navigating very complex settings and environments. But for capturing the intentions and then the future actions of a human agent, and then incorporating that into the rules of how the robot should behave is a big challenge. And this is something that we are currently working on using some of our techniques. And those of you who understand Japanese. Any Japanese speakers here? Excellent. So, and if you're Chinese, you can also potentially read some of these things. So this is a project that we did with Hitachi Corporation in Japan on trying to use the real-time whole body control to reduce the time it takes to do fulfillment in an automated warehouse. And we got a 38% reduction in the time it takes to do pick and place movements. And that comes from an integration of mobile base and whole body movement actions to basically reduce time. So what they used to do was move the base, stop, then do a pick and place, and then move ahead. Whereas if you're able to anticipate where the block, where you want to insert an object is, so while moving, you can insert the box and then kind of keep going. So that reduces the cycle time for such things. So very practical applications. But also, this is an example of application of robots in high-value manufacturing settings where that's what happens now. So traditional jigs, fixed-base platforms, and it's moving towards this. So you can already see robots and humans working next to each other. Where we want to get to is this, where the robots and the humans are working collaboratively in sort of sharing its load, using the cognitive abilities of the human to still do the kind of decision making, but the heavy load lifting and the accuracy comes from the robot. Okay, so switching gears. So I just want to talk about one more topic before I do some sort of live demo. So all the things that you saw before was robots in extreme environments. Extreme environments could be in sort of nuclear setting, could be in offshore oil and gas or harsh environments, could be underwater, could be in space. So there is also a big application of robotics in healthcare and assisted living. And we also do some work in that space. So in a moment, I'm going to get you to try out a prosthetic hand that we've been involved in working with. So prosthetic hands are for replacing upper limb proximity. So if you've lost your upper limb through an accident or by birth, if you've got a congenital defect, then the upper limb prosthetic limbs help you replace some of the lost capabilities, motor capabilities. But before I go there, let me show you some work that we're doing on lower limb prosthesis. So lower limb prosthesis or exoskeletons, they are used for rehabilitation purposes, for support of workers while they are lifting heavy loads, but also for sports injury rehabilitation. So, I thought I had a video here. Oh yeah, that's the video. Okay, so that's the sort of setting we have in our lab with a treadmill, and so one of my ex-PhD students who's now a postdoc is now wearing an exoskeleton with some control wires. Obviously it's a prototype, and they are walking on a treadmill which will detect the forces that the person is applying on the ground. And this exoskeleton is essentially assisting the person while walking. So if you can raise the slope of this treadmill, and you will feel as if you're walking on flat ground, even though the treadmill is raised up, because the exoskeleton is applying force the right sequence at the right time on the legs. So this is an example of shared autonomy where the human muscles are still working, but it is working less because the exoskeleton is assisting it. So if you think about applications of this domain, it can be for rehabilitation of stroke patients. It can be for support of people doing pretty heavy lifting. And surprisingly, NASA came back to us and said, for astronauts who spend significant time in the ISS, what they do currently, because there is no gravity, they have big rubber bands that pull them down onto a treadmill and then have to walk on it. But now, instead of assisting, if you put a resistive setting on exoskeleton, this can act as a way of preventing muscle atrophy, for example. And so let me just quickly go back to this exoskeleton research. So some of the work that we've been doing on upper limb exoskeletons involve getting amputees. This is in collaboration with the NHS, getting amputees to, go do some pick and place of objects based on EMG activation. So this involves amputees pre-shaping behaviors to do some pick and place for, getting objects, picking objects, and sort of navigating the space. And this is for another example where we now, that's more sort of binary. So open, close, this is continuous, this is regression. So classification versus regression in that context. Okay, now I'm going to try and get you to, I need 2 volunteers. If you can put the lights on for a moment. And I'm going to get, I need 2 volunteers to try this prosthetic hand out. So, hands up, who want to get there? That's one. Can I get another one? Okay, good. If you want to come up. Okay, now, you've got to decide who's going to wear the hand and who's going to control it.
I don't want. Yeah, you do that. I'll wear it.
Okay, good. Okay, so I need you to probably remove your jacket because I need to put these sensors onto some place where you can see the skin, so directly onto the skin. So that's good. Okay. So if I don't get you to wear this, so maybe left hand is probably the best. No, it's okay. If you want to tie this up as tightly as you can. Okay, perfect. It's heavier than you think, but now you want to come closer. Oops. And so what you see here, maybe I can just show everybody what, this is an EMG sensor that senses the muscle activity. So what's your name again? William. William. Okay, so it will sense the muscle activity on William's hand, and we will try and see if I can get you to learn how to control this prosthetic hand by using your muscle signals. Try that. Okay, you now want to come across here. If you want to just lift the thing up so that everybody can see, I'm going to turn it on. Okay, try moving just your wrist left and right. Harder, like just go, yeah, okay, all the way back. Okay, again, oh, sorry. Yeah, okay, good. Okay, so you're getting the hang of it. So keep going, just the wrist up and down. Just one direction, yep. One, all the way, keep going. No, just slowly, just in one direction, yeah. All the way. Yeah, and then now go up. Just one direction, just one direction. Okay, now I'm going to try and get you to grasp this. Okay, go for it. Harder, yeah. Okay, and release. The other way, yeah. You can go faster. Good. Okay, so now the good thing is that the hand actually adjusts its shape based on the object that is trying to grasp. So do we have a bottle or something that somebody can volunteer? Or, yeah, okay, good. Thanks. Okay, now you'll see here that, now try that again. So again, so the fingers adjust to the shape of the object that is grasping based on the load, so that this is an example of shared autonomy where he's giving a binary signal of open and close based on his muscle signals. The smarts, the AI in the hand is deciding when each of the fingers should stop closing depending upon the shape and the contour of the object in space. Okay, if you want to try and open it again. Excellent. We'll do one more thing while. So this is an example of a device where you've got a biosignal from a person, you've got the smarts of the AI in the robot hand, but I also have a Bluetooth that I can connect to this. I'm not sure this is going to work today. Yeah, okay, it works. So I can change the mode of operation of this device. So if I now press this, you can see it changes its mode of operation. And now if you do the same thing, the close and, yeah. So that's a pinch grip. Yeah, keep going the other way. So this is an example of a three-way connection between a human, the AI, and the smarts in the machine, and a third-person device using a Bluetooth which can change the mode of operation. Now I've changed the mode of operation again. Now if you do the same thing again, so you can see here it changes its behavior based on the type of objects it needs to grasp. Excellent. That was great volunteering. Thank you very much. I can get you to, yeah, just show it. Perfect. You just drop that here. Perfect. Thanks. Okay, so you've seen already some of the technology that we've been working with, and so again, sorry, can I get the lights down again, please? Great, thank you. So some of the sort of science fiction views about how we may potentially work in the sort of next millennium is no longer science fiction. You can think about a scenario where Tony Stark is sitting in his desk and operating multiple agents and multiple robots from the comfort of his home while giving some very high-level commands, and robots going on and doing its own jobs autonomously or semi-autonomously. So this is not a dream anymore, or at least we're getting closer to that dream. And there are still some very interesting open scientific questions that need to be addressed from a research point of view. We have to ensure safety for these interactions, so safe actuation, dynamic human-robot interaction. This can be in software and in hardware. So some of our work in building hardware that is inherently compliant, so spring-like, so that even if something goes wrong in software, it will not affect it will not harm the person. So there's a lot of work that goes into building compliant systems. Come and ask me, find me so some of the NASA robots, what's unique about it, some of the robots that we do is something called series elastic actuators. It's a very special technology for enabling compliance. The other big challenge is to reduce the sim-to-real gap in digital twins. So if we create simulations, realistic simulations of robots, of objects interacting, it's very hard to model friction, very hard to get accurate notion of how do we interact, how would the model of the world evolve correctly in response to multiple interactions. So reducing sim-to-real gap is a big scientific challenge. And the other thing is understanding the limitations and vulnerabilities of the deployed systems. So how can we build systems that are inherently verifiable, inherently explainable, so that when something goes wrong, we can understand why it goes wrong. So many of you who are maybe in the third year or fourth year, maybe doing some research on deep learning or deep reinforcement learning. The problem with some of the deep reinforcement learning methods is that it's a black box. And if something goes wrong, you won't understand. It's very hard to understand the causal relationship between what's being learned and what the consequence of its actions are. But it's a powerful tool. So the real thing is, can we do something in between where we still exploit deep learning-like technologies, but build in more verifiable and understandable methods into it? So how are we doing this in Edinburgh? There's a little bit of sort of PR thing next. So I direct the Edinburgh Centre for Robotics, which is a joint venture between Edinburgh University and Heriot Watt. And we are very well funded in terms of the robotics labs, and we have something called the CDT, the Centre for Doctoral Training. So this is for postgraduates sort of work in this area. This is fully funded 4-year PhD programs that you pick up any of these domains, that you've seen here. And this is strongly supported by the government. I wanted to put up this slide just to give you another idea of the kind of research. So this is just my group, works on different TRL levels. So if you understand what a TRL level is technology readiness level. So a TRL 0 or 1 is something that is pure research. Something that is closer to 7, 8, or 9 is something that is ready to go to market. And we have different scientific developments at different TRL levels across different domains. So what I'm trying to get at is the science that we do, the research that we do, is not just something that you can write equations and papers about. These are things that translate to real-world impact. Some of them are closer to the market. Some of them are more blue sky research. But there's a scope for any kind of, if you like doing last mile engineering, there's a place for that. If you like thinking outside the box and doing some proof of concept, there's a scope for that. But still, there are some very interesting questions that, as technologists, we need to ask. Are we making the right decisions from a moral and ethical point of view? Are we dealing with security? Are we able to do things like transferring control at the right time? How do we deal with learning systems? So these are all interesting questions that, with my other hat on, as I co-direct the AI program at the Alan Turing Institute. And the Alan Turing Institute is based in the British Library in London. And they are kind of the UK National Centre for Data Science. And I run the AI and Robotics Autonomous Systems program within the Turing Institute, where the focus is not on technology development or algorithms, but the focus is on verifiability, explainability. How do we build trust in robots and humans working together? So those are the kind of hard questions we're trying to ask in terms of accepting, not just kind of pushing technology down somebody's throat, but actually understanding the needs and the fears of people. I'm going to skip this. You can go find out more about the Alan Turing Institute and some living labs in our website. So I'm going to stop here by quoting one of my favorite authors, Arthur C. Clarke. And this quote is very poignant for robotics. So we tend to overestimate technology in the short term, which means if you look at the journalists and the sort of scientists or BBC reporters, or, well, I shouldn't say BBC. BBC actually one of the better reporting. If you look at some of the sort of general news outlets, they want to sensationalize robotics and say that's the next best thing since sliced bread. But actually, there's lots and lots of work that still needs to happen. So we tend to overestimate technology right now. But we also tend to underestimate the impact of this technology in the long term, which means that we have to start thinking about it now, how this technology, this pervasive technology, is going to affect the way we live and play going forward. So I'm going to end here and show you a video of the lab, from our lab, where you have some postdocs, PhD students, researchers, undergraduate students talking about the kind of research that they do. And it's a fun, nice little video that covers everything, more or less the current work that we do. So every year is different, but this is shot very recently, and so it'll be a fun video for you guys to watch. Welcome to the Statistical Machine Learning and Motor Control group at the University of Edinburgh. Here we do exciting, world-leading research on robotics, machine learning, and data-driven techniques using artificial intelligence to make robots a lot more versatile and adaptive to the real-world situations. We do work across domains, so applying the core problems in robotics and machine learning to domains in oil and gas, transport, healthcare, as well as things like the challenges of exploration in outer space.
We want our robots to be autonomously deployed in industrial plants, for instance, to perform inspection tasks, to accomplish tasks that humans can't do or that are dangerous for them.
Our main business is to educate the next generation of outstanding postgraduate students and conduct cutting-edge research.
My research is focused on designing exoskeleton controllers that can assist people completing tasks such as walking. And to achieve this, what we do is we build quite complex neuromuscular models of human subjects. and combine this with a very detailed set of motion data that we can collect in our gait lab.
We hope that with this setup and combining robotic assistance with electrical stimulation, physical therapists can have a tool to personalize the intervention and improve the outcomes of physical therapy.
My research is about robot localization in changing environments. When the robot's view is nearly occluded by large moving objects.
We want the robot to learn which objects are of interest without requiring a human to provide information about the shape or the visual appearance of these objects.
In order to enable robots to move while in contact, for example, when wiping a table or pushing a heavy object, my research focuses on how to plan or how to learn those types of physical contact interactions.
We are developing mathematical models to enable a robot to capture heavy and moving objects with 2 arms. At the same time, we are handling impact.
My research involves both humans and robots, where first we enable the robots to predict humans' intentions and actions, and we also generate safe robot actions in order to help the humans reach their goal.
In construction, robots are often operated by humans in dangerous environments, needing expensive training. To reduce the operator burden, I'm working on shared autonomy, which combines human input and autonomous methods so the human can best utilize their expertise.
I'm really interested in human-robot collaboration, so how we can enable robots to perform a common task effectively with human, such as pouring a wine into a human's glass. But humans are really difficult to predict, and so I'm interested in how we can better make those predictions.
I'm working on the development of robots that can be easily taught to manipulate objects and potentially collaborate with people or assist people in need just by giving a demonstration of the task.
I'm working on leg robot to make them traverse challenging terrains. The idea we propose is to start with a capable controller that already works on the robot and try to extend and add capabilities to make the robot cross challenging terrains.
I'm working as a software engineer in a field robotics lab, and also I'm doing some research about quadruped robots. I'm working on how those robots with 4 legs should plan their footsteps considering the torque limits on their legs.
When robots have to perform manipulation and walk simultaneously, they face a lot of uncertainty. One way we can increase the robustness of the system is by taking into account the capabilities of the robot, so its motors and also the contact stability.
There are many conditions that we cannot predict. For instance, when we are navigating in an offshore platform, we might encounter a floor that is wet. A way of dealing with this kind of uncertainties is by replanning quickly new motions.
I'm working on building better robots for specific tasks. So a robot that walks might need to be built a little differently than one that jumps. And so I'm working to create algorithms that modify the designs based on the tasks. And I'm looking at making those more efficient and physically realistic.
My work focuses on motion planning, especially when it comes to the environment changes, there are either obstacles coming in and out or the objects that the robot is trying to pick up and move are moving. And this is especially useful when working with robots that need to be safe around people and other robots.
So the environment may have many different inclined slopes, and this gives rise to a lot of different options of when to play the foot and where to play the foot.
Robots in the real world have to operate in environments where obstacles around them are moving. So whether that's in hospitals where we have people moving around, or whether that's in a factory where you have other robots that you might need to avoid. My research interests are in developing algorithms and motion planning software that will allow us to move robots in ways that avoid those obstacles.
I've particularly enjoyed working on the large-scale projects which we have within the group, and helping with the project management side with the Alan Turing Institute, the ISCF hubs, and also the EU Horizon 2020 projects.
So if you've liked some of the research that you've seen in the video and would like to work on some of these exciting platforms and projects, please do get in touch with us, and we'd love to have you as part of our team. Okay, thank you very much.
Yeah, so if anyone's got questions, just go ahead and put your hand up.
Yes. Sorry? Yes. Yes, the NASA robot's still here. Absolutely. If you come to the atrium of the base building, you should be able to see it. Any other questions? There's not. It can be, completely right. Right. It doesn't have to be related to what I just showed. So, go ahead.
So, what areas specifically are you working on right now?
So that's all. So all of that is work that I direct. So it's a bit crazy, but I've spent my sort of 15 years, close to 20 years now, since I was a master's student working on robotics. So the core aspects of all of these things are algorithms that connect perception to planning to control. So although you've seen a variety of platforms and a variety of things, but the core fundamentals are developments in those three areas, connecting perception to action. As our projects roll, we deploy it in different settings and different environments, but fundamentally, they are still the same in terms of the core developments. So I would say I've been working on this for the past 15, 20 years algorithmically, but been deploying it on different use cases, different domains, different robots. Yes? Sorry, I can't hear you. Maybe should we use the microphone?
Yeah, so you mentioned, so I noticed that there was not much mention of AI except for some deep learning in some areas. So how much AI is actually involved in all this perception? And by AI, I mean things like neural networks and machine learning models, like how much of it is involved in these perception processes?
Okay, so these days, machine learning and AI and so data science is all very interchangeably used across the field, especially for people who are slightly out with the domain. They don't find a big difference between these terms. But in reality, so machine learning is a paradigm. Data science is a bigger area that utilizes data. Neural networks, algorithms, deep learning, so those are all methodologies within that paradigm that uses data to do something clever. So if you go back to robotics, so the kind of things that we focus on, we use traditional methods like the model-based control, the physics-based models to do things that we can do, but then we use machine learning and data science to learn the uncertainties, learn the mismatches, learn the differences between the, so to say, the sim to real gap, reduce sim to real gap, using AI-based techniques. So there are other people, other groups who work in a slightly different way. They'll try to evolve behaviors, learn something completely from scratch, and ignore the physics, ignore, putting gravity into the model. But I personally feel that's a very highly inefficient way of doing things, because if we know there's gravity, we might as well put it in and then learn the mismatches rather than having to collect tons and tons of data to be able to discover gravity. Yes.
Thank you for the presentation today. I see that you're very active in terms of outreach to undergraduate students. What can undergraduate students do to broaden their vision and to discover potential research interests like this?
Yeah, thank you for that question. And you're absolutely right. I'm very passionate about outreach, not just to undergraduate students, but I've been sort of going out to schools. I've been involved with the Edinburgh Science Festival since about 2009. So pretty much every year, me or my group does something at the festival. So I think it's very important to get that, get that excitement across, because in some sense, to get to some of the work that I showed you here, there's a lot of building blocks, starting from things like being quite comfortable with continuous maths, and being quite comfortable with, say, I wouldn't say differential equations, but things which you should be comfortable with differentiating through a chain rule, things like that. Things you learn in school, but then you tend to forget once you're in university. If you end up sort of pulling stuff from GitHub and sort of implementing things and running things, so sometimes you tend to lose track of some of the fundamentals. And from that point of view, I think I want to get across the fact that the basic core science and the maths and the physics is still very, very important, because some of the problems that we face when we pull, say, a computer vision algorithm, and it works for certain cases, doesn't work for some other cases, and we try to diagnose why that is the case, you need to have a fundamental understanding of ray tracing and refraction and diffusion. So that is the kind of message I try to get across to the younger generation. It tends to be this. Well, it may seem like I'm kind of rambling about this, but it seems like a quick gratification by pulling things from some database and sort of implementing things and showing, wow, my algorithm works, here's a database, here's my project. But if you sort of dig a bit deeper into some of these core things, it'll hold you in better stead in terms of making fundamental progress. And that's the kind of things I would say I would advise the students who are involved in. So in terms of getting projects, I would say it doesn't matter if you are part of a small cog, but as long as you understand that particular cog that you're involved in quite deeply, that would be very, very useful. Yes. Oh, okay, one there.
With the NASA robot, why is it specifically a humanoid shape? I mean, would that design still be effective for a planet with a very different atmosphere and gravity compared to Earth?
Yeah, so the humanoid, I get asked this question all the time, and so the humanoid's form, if you look at the NASA, I should have actually a very nice video or a picture I took when I was at the Johnson Space Center, and it was this kind of aerial view of all the robots that they have, and the humanoid just forms maybe sort of 10% of the kind of robots that they have. They have wheeled systems, they've got quadrupeds, they've got spider with 6 legs, so it's horses for courses. And so the humanoids are a particularly challenging variety of robotic systems that are designed for work in human-like environments. So steppes, narrow environments like the space station, where the problem is, if you've got wheeled systems, you need larger wheelbase, you cannot have steps, you cannot have holes which you can step over, you cannot squeeze between environments, narrow environments to reach for things. So effectively, the humanoids are mainly designed for working in environments that are built for humans, but it would not be appropriate to send a humanoid out to walk on a dusty Martian surface. You would potentially use wheels or something more robust in those settings. But funnily enough, Airbus were very interested in a project with us using humanoids, because they said that when you are retrofitting or when you're fitting a new Airbus hull, where you have to do flexible wiring, and the people have to kind of squeeze under stand in a very weird pose and sort of do all these things, and there's human error. They wanted a humanoid system which does not take a larger wheelbase or space than a human would, but will have the versatility and the multi-contact abilities to do this for human-like tasks. And that is the reason why we're doing humanoids. One up there.
Sorry, we're actually going to have to stop questions now, but we're going to have a break for food. I think you're sticking around for a bit, so anyone can just ask him directly.
Excellent. Great. Thank you very much.
everyone, could you please go back to your seats? We'll just be starting in a couple of minutes.
I'm not sure if they can hear you.
Could everyone please go back to their seats? Okay, everyone, so could we please have a warm welcome to our second speaker today, Dr. Petros Papapanagiotou.
Right, thank you very much. Thanks for staying after pizza and after a very amazing talk about robots that go to Mars and so on and so forth. So hopefully I'll be able to inspire you with some of my own motivation and my own passion for research. Thanks also for the valiant effort to pronounce my surname. So I'm Petros Papapanagiotou, and I'm a Chancellor's Fellow in Digital Technologies. And I'm going to talk to you a little bit about the combination of processes and data, specifically in socio-technical systems. So what even is a social-technical system? So I'm going to try and give 3 examples just to show you what kind of domains we're talking about. The first one is in a hospital, where you would usually have some medical staff in the middle, some doctor who has to interact with a lot of different things. First person who have to interact with is the actual patient. There's going to be some data interaction with that patient, collecting information about what's wrong with them and so on and so forth. Then they're going to have to follow some policies that they have to learn about how to do things in a hospital, what kind of rules they have to follow, what are the procedures they have to do, apart from the years and years of studies that they have done. And then they'll have some electronic systems, some databases, medical records, forms processing, all sorts of electronic systems that they have to use. Then they have to talk to other people. They have to collaborate with nurses, with other clinicians, with the medical team, with admins, with a bunch of other people. And they also have to work with different services, with the pharmacy, and that also involves other types of people, other types of systems, the surgery, and so on. And last but not least, we're moving towards a data-driven kind of society and economy where we have sensors everywhere and lots of data coming in and lots of new information that wasn't previously available. Now we have to do this as well. So now you have this doctor in the middle who doesn't really know how to deal with all this, and they have to put all this knowledge and how to use it all in one brain. And even worse, you have this patient up there who doesn't have visibility to any of these things, and they have to understand what's going on. And how often do you find yourself in a hospital or someone you know in a hospital where they're just waiting for things to happen and they don't actually know what is going on? Another similar environment is a factory, which we also have worked with, where you have production of different things. And we've moved a lot, for a long time we've been moving away from continuous production of large scale of the same thing, of big pens or something like that, into small batches of what we call Agile Manufacturing. So the idea is that you have small orders that are sorted in different production lots and go through different groups of machines in the factory that do perform different operations, and each production lot will have specific operations that they need to apply based on the different things they're producing for the particular order. Each operation can last 6 to 8 hours. You're looking at the washing machine there for some metal parts. This is a pen factory, by the way. And most importantly, even though we have all of this machinery going on, all of these things are manually performed. You need an operator to perform the operation in the machine for several hours, and the scheduling and the movement around is also done manually by humans. So now you start seeing humans and machines working together to achieve what they want to achieve, which is what makes a socio-technical system. And last but not least, in the interest of time, I'm not going to go through this particular example, but you've all heard about social networks, for example, which have now started expanding in what we call in a social machine, where again, the machine has started having input and feedback into this process. So we've gone past the social network where simply humans are interacting into a network where humans and machines are working together. I don't know if any of you recognize any of these. Some of these are mostly on the social network side of things, like Stack Overflow or Wikipedia, where people come together to bring this, the knowledge together. But we've got things like the weather signal, where we have sort of a crowdsourcing of temperatures, and the machine does a lot of the work to produce the temperature across Scotland, for instance, in different parts. So for example, you have to reject people that just give random temperatures and so on. So there's a lot of processing there and so on. So the problem is that you are sitting in the middle of all of these different components as a person, as an actor in one of these social technical systems, and you have to interact with all of them, and sometimes you won't know how, or you won't even see how. And the other problem is that although there is a bit of effort to try and give control back to the user, so re-decentralize the web is what we call it, where we take up the power away from the big corporation or the centralized system, and we try to give it back to people so that they control their own data. But the problem there is that even though we understand how data circulates and we focus on the data, we lose sight of what happens to the process. How is the data used? What are we actually doing? And how can we model that and streamline that? So what I want to focus on is to shift this into a solution where the protocol, the process, the way that we want to work, the things that we want to do, sits in the middle, and everybody interacts with that in a way that we all understand how we're interacting, and the machines can also understand how they are supposed to interact, and it's all transparent, and we can verify that it's correct, we can optimize it, and we can do all sorts of interesting things with it. Three major things we need is for all of us to be able to understand that. So it can't just be a black box that spits out instructions that we all need to follow. We need to be able to trust it, so verify that it does what it says it does, test properties about it, and so on. And also decentralize it so that it's not just one entity in the middle sitting and telling us what to do. It's actually a community of people and machines, or a network executing it. So here's what my work is about. My work is creating workflow models, so models of these processes that I'm talking about, and bringing in formal methods, specifically theorem proving and logic-based methods, to produce a system to support some of these functionality that we're looking for. So in terms of the workflow modeling, we're looking to build process models that look like this, basically glorified flowchart, you could call them if you want. And the idea is to try and map out and clarify what a process looks like. For example, what does the doctor need to do from the moment the patient steps into the hospital until they are discharged? And capture all this know-how that's implicit in people's brains, and they know how to do things from experience. Now we want to capture it in a process model that we can actually understand. And we want to support its execution so that machines can support what needs to happen at every given state, so that, for example, the doctor can focus on what they need to do instead of what comes next, or who they need to talk to next, or what kind of coordination they need to do. And then, if you have this kind of computational model of what is going on in your process, then you can start asking questions like, what if we change this? Or how will we schedule these processes given a limited set of resources or a limited number of doctors, and so on. And we have this kind of idea of iterating, further improving the models, and try to optimize them so that they are more efficient and that we can work better. Now, using logic behind the scenes, and of course this is going to be a 2-hour-long lecture about logic, as you imagine, but no. So it's not just a visual model, it's not just a flowchart, it actually has a formal underpinning. So it has a logic behind it, and we use process algebras, or what we call session types, to have a semantics about it that the computer can understand and execute. And we can also analyze and verify it, and specifically executed in a distributed way, which was one of the things we wanted. So I'm going to try and show you and take you through the whole journey from designing a model all the way to how we get to use it in practice. And these are the main steps. So the first step is about modeling. So it's about creating the model. So we have this tool that is part of this Workflow FM set of tools that we have introduced, where you start introducing these simple steps in your process. So the most basic steps that you can have, and then you start and you specify them based on the inputs and the outputs. That's how the model works. You specify the things that need to happen for one step and the outcomes that come after you execute that step. And then you start plugging these together to form complicated workflows where the resources flow from one step to the next. And of course, as I promised you, this is not just a pretty image. Actually, behind it, there's logic. So everything that you do translates into a logical underpinning, into logical specification, even though you just see the picture in front of you. And that gives you a lot of guarantees in what we call correct by construction modeling. So as you're building the model, the logic guarantees you that you're avoiding certain types of mistakes and you're getting some nice properties. I don't want to go through much detail. This is just one of the atomic boxes that you could come up with, and you can specify inputs and outputs of different types of resources or different things that need to happen. And we can support also these dashed edges that you see on the left is because you can have optional stuff happening. So you might receive either a Y or a Z, and you might produce something or something else, or you might have the outcome that you wanted or an exception. And again, as I promised, there's logic behind that. So I have here a small example just to show you, just to give you an idea of what the logic does for you and why do we need the logic. Because if you just open any kind of diagramming software, you can just put any boxes you want together and connect them in any way. But in this particular case, we have a very specific way to connect these processes. So you'll just plug them together, but the logic will give you this. So here's the example. Assume that we have one process, it's a hypothetical one, in a healthcare scenario where you need to deliver a drug to a patient. And in order to do that, you need the information about the patient, who they are, where they are, what's wrong with them, and so on. You need the dosage of the drug, how much of the drug you're going to give them. And you need some time to allocate for the nurse to go and deliver the drug. So that is a resource that you need to use for this step to take effect. And the outcome of that step is that either the patient was treated because the drug worked and we're all happy, or for whatever reason, the drug failed. Right? Very, very simple example just to show you. And then there's another process where it's like a contingency process where if the drug failed and it didn't succeed for whatever reason, then we have this outcome failed over there, and we also have some time that we reserve for the clinician to come and check the patient and reassess what happened. And that is also a resource that we need to use. The time is valuable, of course, right? And the outcome of that process is that the patient is checked, whatever that means, right? I don't want to go into too much detail, it's just a simple example. So the question is, if you plug these two steps together, so if you plug the fact that the option that the drug failed into the input for this process, what is the specification, the input and the output of the two of them together? Now, intuitively, you would say, okay, either the patient was treated in the first place, or they failed and we ended up checking them. So that's the two possible outcomes that we could have. But actually, that's not right. Because if the drug succeeded, then you never did the reassessment. So that extra time of the clinician that you have as an input, which is still an input of the joint process, is still a resource that you haven't used. And the logic gives that to you automatically. So it calculates all the resources that you haven't used and gives it to you automatically. So in the system, you just join the failed on the left with the failed on the right, and the system automatically gives you that without you having to do anything else. And of course, there is a detailed breakdown. This is just a collapsed version, but you can also see how it's connected together with a slightly more complex diagram. And again, as I promised, all of this is logic in the back. Of course, you don't have to do any of this manually. It's all automated reasoning. It's all happening, but it's all happening in a theorem prover, fully verified and as secure as it gets, basically, or as verified as it gets. So now we can come up with some more complicated workflows. This is one from the manufacturing example that I talked about, where it's a simple reserve, buffer, move, perform kind of pattern where every step of the manufacturing process, you need to reserve a machine to do that step. If the machine is busy, then you have to move your production lot somewhere where we call the buffer zone, where it just sits until the machine becomes available. Then if the machine becomes available, you move the production lot to the machine, and then you perform the operation. And that is sort of the unit pattern for one operation in the factory. Right, the next step now, once you have this model, okay, now we drew a nice diagram. We know that it's correct to some degree. It calculates the resources for us. The next step is to try and deploy it, actually execute it, to be able, I promised you that the machine, I can understand it and execute it. So this is accomplished by a very nice theory that is called proofs as processes. And this theory says that with this particular logic that we're using, any model that you build with it can be translated into a process calculus term, which is basically a term that can be executed by the machine. Now, how great is that? We didn't have to do anything. Just with the theory, we get the term. So in this particular example, this is what the process calculus term looks like. And of course, you're not meant to understand it. The machine has to understand it. But because we use the formal theory, we can trust 100% that this process calculus term operates exactly as we want it to operate and as the visual model that we built. So we're getting all of these things for free. And of course, you can imagine that as soon as you start extending and building bigger workflows, the process calculus term becomes bigger. This is an example from patient handovers. So one doctor passing on the patient to another doctor for another specialism. So we build a pattern like this. And even bigger and even bigger. This one is from a care pathway that we modeled for HIV patients here at Chalmers in Edinburgh. So this is the main idea of what happens in deployment. The idea is that you started from the very left, and you introduce those simple tasks, the basic components of your workflows, and you combine them together to build your models. Now what happens is that this combination, the code that plugs together all your components, is generated automatically in Scala. I don't know if you've heard of the programming language, right? Now, the only thing that's missing to complete the execution is that you need to provide some implementations for these black boxes that you introduced in the beginning. Because you just told me a black box with some inputs and outputs. Now you need to give me and tell me how that works. And we do provide some traits, some abstract interfaces, basically, that you need to implement to guide you to make sure that you have the correct resources and all that. But then you have to fill in the implementation yourself. Here's an example of how this template would look like for this process that I showed you earlier. And again, I don't want too much detail, but this is in Scala, but even if you've done a bit of Java or something like this, you could recognize what this means. So this one translates into a function that takes one argument of type X, because your first input there says it's an input of type X. Then it takes another argument that's either Y or Z, because that's an optional input right there. And then the output is a tuple, or a nested pair, if you like, of A, B, and C. And finally, you also have that future word there, which is what allows us asynchronous execution. So this function doesn't just return the stuff immediately, but it can go and do some asynchronous calls to a web service, or even to something that takes very long time, like a manufacturing process, or even ask a human and wait for human input, and then it will return at any point. But thanks to the theory, we don't have any race conditions, we don't have any deadlocks, no live locks, it's all working. Right? Now we have been doing some work to try and make this even easier, so you don't have to write any code, or at least what we call the low-code solution. The idea is that you can build some of your processes in advance in Java or in Scala, and you create a jar file with them, and then you load it into the system, and now you can map these processes directly to tasks in your workflow. But this is work in progress, but Now the next thing that happens, and let's see if this will work. It never works when you want it to work. If it did work, this would show you some location tracking that we did in the factory that we worked with. So we installed location tracking using Bluetooth. And if this was working, you could see the video where you could track where the production lot is going through in the factory. So now you can monitor what's happening in the physical world and map it to your workflow and start asking questions like, are we doing the right thing? Are we moving it to the right place? Are we following the workflow, or are we making any mistakes, and so on and so forth. Of course, in practice, things become a lot more harder when you start realizing how the sensors are not that great all the time. So both of these that you see here are full production flows that went through the entire factory, but that's the only thing that got recorded. So in the first case, they just went into this buffer area and this just stopped there. In reality, it did go through the entire factory, just the sensor failed. And in this case, again, there was a bit more movement. It actually left, this shows that it left the building. So this is the wall of the building. If we followed the sensor blindly, we would think that it went through the wall outside the building and then back in. So you have to deal with all this noise and process and analyze this as much as you can, to understand what's going on. Another way of tracking what's going on is with checklists. So we have ways of generating checklist templates from the processes. And we actually have some students working on some of the implementation of this right now because it's still a design. But it's very important to be able to interact with the humans. Remember, we said this is a socio-technical system, so we want the humans to be able to give you feedback. And we did do some work with design checklists in the healthcare scenario, and we evaluated this with actual clinicians about how they transfer patients, specifically for tracheostomy operations. The last way that I wanted to show you quickly about how you track things is with what we call shadow institutions. And this is an example from another piece of research that we did, another paper, where we have people interacting on Twitter, and they just talk about arranging a meal or an event, if you like, and then we have the machine sort of shadowing this interaction and mapping it into a workflow that helps them coordinate to arrange that meal. So without you doing anything else, just normally interacting, the machine can help understand what workflow you're following and help guide you through it. Now, once we have this tracking and this deployed models, now we can start getting some interesting monitoring, interesting analytics. So this is a bespoke dashboard that we built for the manufacturing example. You can start looking at timelines of productions, for example, of workflows. You can start looking at analytics of delays or bottlenecks, things like that, notifications of things that are going wrong, and so on and so forth. The last thing we can do is we can start simulating, because it's a digital artifact, we can execute it. So instead of executing it in the real world, we can execute it in simulation. And we can use this in this example to generate, for example, we had a virtual model of how many machines the factory has and what types they are. And then we drew from their resource planning system the orders that they had for the next week or so. And we put that in the simulator now, based on how much the duration of each operation lasts. And now we can get a prediction of how the scheduling might work out. And this is a work from another student of mine who tried to use this data from the simulator to create a delay analysis and try to create explanations about what is causing the delays. For example, in terms of informing, say, you need one more machine for this operation because it's causing a lot of delay, that kind of stuff. And this is another paper that we published again in the same domain where we tried to predict the scheduling. So we had a list of jobs over a whole year for one of the factories that we worked with. And we tried to predict how long things would take, the scheduling, compared to the actual delivery time, and compared to what they had planned, what the manager planned when they started. So when they start and they get the orders, they try to plan ahead how long things are going to take. So we compared to that, and the yellow one is us. Closer to 0 means better because we had better accuracy. So with a very simple simulation model, we got much better results. Now with this slide, I don't want to go through the whole architecture of the system, but the thing I do want to point out is that, so we have the modeling part on the left and the execution things on the right with the workflow engine and a simulation engine here. But the blue parts and the blue parts on the left and the green parts are all open source. So all of this software is available online and for anybody to use. And we're doing a lot of student projects on that. Michal is up there doing part of this work as well, for example. So we set up a lot of student projects on this because there's a lot of interesting work to be done. And by the way, if you're interested in this kind of stuff, we do plan, nothing, it's not confirmed 100% yet, but we are planning for an spring internship. So keep your eyes out for that. Now, before closing, I wanted to mention one more piece of work that's relevant to processes and data. And this is linked to another type of work, a whole project that is called the Advanced Care Research Center here at the University of Edinburgh, which is a big project that covers a large multidisciplinary team of researchers from the medical school, from social sciences, engineering, and informatics. And the goal of this project is to provide better support for people at a later age. And we're specifically interested in people's independence, where they're living at home, so care at home setting, or care home setting, so if it's an organized care home that they go to. So this particular strand of work has to do with creating process models, like the one you see at the bottom, of the routines, of the daily routines of these individuals. And to accomplish that, we get smart home sensors and that track how people are behaving in their homes. And we can deduce from that, using machine learning and activity recognition, we can try and deduce what sort of activity they're involved in, whether they're eating, sleeping, cooking, reading, and so on. And by mining this data, we can produce this kind of workflows that correspond to the daily routine of this individual. And once we have that, now we can start exploring and analyzing this compared to more data that comes in to see if there's any deviation. So if we start seeing deviations, we want to see whether these deviations are mapping to some health problem. For example, if their sleep is declining, or they're not eating as much as they should, or they are not taking their medication and all that stuff, all of this can be detected from the workflow. So this, for example, shows you a deviation in the sleep pattern where it dipped in a particular day. And this is a long-term kind of pattern where it's slowly declining for some reason. So we're analyzing this type of data. And in the future, so this is inspired from another paper that's not from us, but we want to be doing the same thing with much more expressive workflows, where you can start having interventions. So identify the right parts of the workflow where you can have an intervention. For instance, if people want to sleep early, research has found that just sending them a notification when it's time to sleep, go to bed now because it's time to sleep, doesn't really work. No one likes that. But instead, you could do something else, which proves to be much better. You can tell them, you know, it's 10 o'clock now, maybe you should have dinner now. And by asking them to have dinner earlier, that leads them to also sleep earlier because of their routine and what they follow. So this is the kind of behavior that we want to try to use in the advantage of providing this kind of service to the people who want to keep a healthy life. Now, before closing, I wanted to give you something that's a bit more general. It has to do with how do we accomplish all these things, because all of these are very applied things that are focused on specific domains, and it has to do with understanding the processes and the way people work. And this is the typical computer science stereotype. I'm sure you've seen this picture before, or some of that, where you're just sitting in a room and coffee comes in and code comes out. And of course, this is no longer how things can work. If you want things to work, at least in this kind of domain, you want to be working with the individual person that is interested in what you're doing, that is going to be benefiting from what you're doing. And perhaps a lot of software jobs are still like this. So you're just in a room, they have your morning meeting, you do your sprints, and then you don't have to talk to anybody else for the rest of the day. But if you're going to be an innovator, entrepreneur, or researcher, or anything like that you're designing new things, it's much better to design them working together with the people involved. And of course, I think the funniest part is not this picture, but rather the top Reddit comment, which is also quite funny. And then we also have to make sure that we bring down the the stereotype that non-computer scientists have about what is possible to do and what isn't, and how easy certain things are and how difficult they might be. So that's all I had to say. Thank you very much, and I don't know if we have time for any questions, but thank you. Thanks for having me anyway.
So unfortunately, we don't have time for any questions. So if you do have any questions to ask, please come up and ask personally. So thank you very much for coming tonight. Hope you had a wonderful night and enjoyed the pizza. Thank you very much.